Okay, in this chapter we're gonna cover turning and hole making. We're gonna take a look at machining processes that are capable of generating round external and internal shapes. And the most common machine tool used for the operations is the lathe, and available in several types and degrees of automation. We're gonna learn about different types of operations that can be performed on lathes, such as turning, drilling, profiling, facing, grooving, etc. And then we will describe operations such as boring, drilling, reaming, and tapping. This chapter will describe processes with the capability of producing parts with rotational symmetry. This, for example, screws and turbine shafts for power plants, rolls for rolling mills. These are some examples. And most basic machining process is turning, where the part is rotated while it's being machined. So the part can come from your workpiece or your blank can come from various processes like casting, forging, extrusion, drawing, etc. So these operations, these turning operations, they are again performed on lathe, like the other operations we're gonna see, using machine tools. So the turning operation, it is where the workpiece is rotated while the tool is moved, and with this technique we can produce highly versatile and wide variety of shapes. And here is the turning operations A and B, and again all of the examples, the videos of these operations are available to you. If you want to understand more and visually see, please don't forget to watch them. And as you can see in image A and B, describes us the turning process, and here basically the part is being rotated, as you can see, and it is being machined. Another process is facing. Facing is done to produce a flat surface at the end of the part. Here you are seeing facing EF. We are seeing it is producing at the end of the part, it is producing a flat surface. And in image F, we are seeing face grooving. Face grooving is producing grooves for o-ring seats. Machining with form tools. Machining with form tools, this is to produce various axisymmetric shapes for functional or aesthetic purposes. And let's take a look at that. Where is it? By the way, turning operations cover from A to D. So A, B, C, D. All those are turning operations. E and F, they are facing, and G is where we have the image of machining with form tools is showing up. Next is boring. This is to enlarge a hole or a cylindrical cavity made by a previous process. So in this case, you already have the hole or the cavity made previously and you enlarge it. So you are seeing it in image H here. So already prepared hole, and you are making it larger. Another type of process is drilling, and we know drilling is done to produce a hole, which may be followed by boring to improve dimensional accuracy and surface finish. So if you watch the videos, first you will see that first they do drilling to form the hole, and then do boring. They can either do it to enlarge the hole, or they can do it to improve the surface finish or dimensional accuracy. And drilling is just illustrated right in the image I. And there is also cutting off, or what we call parting. This is to cut a piece from the end of a longer piece. So image J is showing cut off. Threading is to produce external and internal threads, and we are seeing this illustration in image K. Knurling is to produce a regularly shaped texture on cylindrical surfaces, as in making knobs and handles. As you can see here, this is your tool, and that is producing texture on the surface. This table summarizes machining processes, and here we're going to see in this chapter turning, boring, drilling, and we will see the other ones later on. And this is just summarizing you the characteristics of those processes. And this is a typical lathe machining operations that we have just described. They are performed on a lathe, and these lathes, they are available in a wide variety of designs, sizes, capacities. They can have computer controlled features. So turning operations can be performed at various rotational speed of the workpiece that is clamped. So the rotational speed is n, and that's a parameter that affects the turning operation. And there is depth of cut we have seen, and it is represented in image B, as you see that with the lowercase d, and we have seen this in the previous chapter. And there is the feed, is the F, right? And there is also different types of cutting fluids available to provide better cutting conditions. So it helps, some fluids helps the removal of the chip. Okay. What are the forces in turning? So there are three principal forces acting on a cutting tool that are important in the design of machine tools, deflection of tools, and workpieces for machining operations. So the first one is cutting force, FC. This cutting force, as you've seen in the image, acts downward on the tool, and it tends to deflect the tool downward. And another force is thrust force, FT, which acts in the longitudinal direction, also called feed force. This force tends to deflect the tool towards the right, away from the chuck. So this direction. And radial force, Fr, acts in the radial direction and tends to deflect the tool away from the workpiece. These forces are difficult to calculate directly because there are a variety of factors affecting the process. Therefore, these forces are calculated experimentally. So why these forces are important? Because the machine tools and its component should be able to withstand these forces without undergoing significant deflections, vibrations, and chatter. The forces also will tell you information about the power required in the turning operation. So what is boring? Remember, we described this before. Boring enlarges a hole that is previously made by another process such as drilling, or it can produce circular internal profiles in hollow workpieces, and it can also provide better surface finish. So the cutting tools that are used in boring are similar to those used in turning, and they are mounted on a boring bar. Boring bar, they have been designed and built with capabilities for damping vibration. It is essential for the boring bar to be stiff to minimize tool deflection and vibrations. This will help with the dimensional accuracy and surface finish, which is the main goal of boring process. And for that reason, a material with high elastic modulus, such as tungsten carbide, is desirable. Here in the illustrations, you are seeing a steel in image A, steel boring bar with a carbide insert. And again, this is done to provide a vibration resistance, damping the vibration. And then there is the coolant hole that is used to cool during the process. And also there is image B. Sometimes they put tungsten alloy discs within. This will help to counteract the vibration and chatter while boring, because these are the devices that provides dimensional accuracy and surface finish. We need to be careful about damping the vibration. Drilling process. We know hole making is among the most important machining operations. And why do we make holes? Holes are used for assembly with fasteners, for design purposes, or for appearance. And drilling is a common hole making process. So drills have high length to diameter ratios, and they are capable of producing deep holes. And because of their high ratios, that makes them flexible and prone to fracture, and they can make inaccurate holes. In addition to that, if you watch the videos, you will see the chips will be produced, and this can present difficulties while they are disposed from the hole while it is being drilled. Here we are seeing one example of a drill which called chisel edge drill, and you see the shank, this portion, and that is where the drill is clamped, and it can be straight or tapered like this one. We also see the body. It is the portion between the point and the shank. You see here flutes. These are 2 or more spiral grooves that run the length of the drill body, and they have some roles. If you watch the videos, it's explained clearly. They make the chip easy to remove from these channels. So when it is being drilled, these are the channels where the chips can escape, and they also curl the chip tightly for easier removal, and it allows the coolant or lubricant to get down to the cutting edge. We see body clearance that is here, and it is the part of the drill body that has been reduced in order to cut down friction between the drill and the wall of the hole. So there are different types of drills, and twist drill, the one we have just seen the example of, is the most common type. And generally they have 2 spiral grooves. 2 spiral grooves means flutes. Here you are seeing an example. And there are core drills. Core drill is used to make an existing hole larger. This one. And there are step drills. These produces a hole with 2 or more different diameters. Here you can see. And then we have counter boring and counter sinking drills. These produce depression on the workpiece surface to accommodate the head of screws and bolts. Here. And there are gun drills. These are for drilling deep holes, and it requires special drill as shown in this image. And then center drilling, that is used to produce a hole at the end of a piece of stock so that it may be mounted between centers in a lathe. So you are seeing all of them has different purposes. And there is the spot drill that is used to start a hole at the desired location on a surface. So a reaming operation. A reaming is an operation used to make an existing hole dimensionally more accurate, improve surface finish, and this is achieved with a reamer, which is a multiple cutting edge tool with a straight or helically fluted edges that remove very little material. And if you watch the videos, you're gonna see yes, this removes very little material. It provides better surface finish, and we work on an existing hole to make it more dimensionally accurate. And So the terminology for that reamer is given in this figure. You don't need to memorize these, but if you are interested you can learn about it, but I don't want you to memorize any parts of these. It is difficult to keep these things in mind. And then there is tapping. So internal threads in a workpiece can be produced by tapping. Basically, a tap is a chip producing threading tool with multiple cutting teeth, as you are seeing in the images. It has 2, 3, 4 flutes. Here the chip removal is a problem because as you can see there are smaller clearances in the tap, and this will create problem because the chips, if they are not removed during the operation, it will increase the torque, the power, and it can break the tap. So that's it for this chapter, and for the exam will be until the end of this chapter. Okay, so I will make you guys an announcement. We will not include the Monday's class in the exam. And don't forget to watch the videos after reading through these lecture notes and listening to the lecture.